Okay, so now let's look at a very similar case. We're again going to visualize the execution of the queue as a finite state machine, but now we're going to have a much larger queue. We're going to have a queue that stores 1,000 elements instead of 2. So we're going to have exactly the same kind of state machine, but its shape has changed. Instead of containing 3 nodes, it contains 1,001, and so I've left out a vast array of states in the middle. And so when we randomly test this queue, we're still going to start at the empty state, but let's look at what the dynamics are this time. So here I have a queue with n equals 1,000, and nothing else has changed. So I'm going to run the random tester. And this time we've done around 50,000 adds to a non-full queue, and we haven't done any adds to a full queue. We've done almost 50,000 removes from a non-empty queue and 10 removes from an empty queue. And so let's try to understand what happened here. So what happened is, and I'm going to come up with another view of that state machine. So here we have the empty queue, and here we have the full queue. And here we have the number of times we visited a particular state. And what's happening is, with 50% probability, we're randomly walking back or forward, and we're going to be getting a situation where the probability of visiting queue states farther away from where we started drops off exponentially. And actually, there are good closed form equations for computing the probability of getting to any particular point. But as we saw, using 100,000 tests, I believe, we never actually managed to make it to 1,000. Although we did perfectly easily make it to a queue size of 2. And so 1,000 isn't a particularly large size for a data structure. We could easily have some sort of a queue that held 10,000 or 100,000 elements, and the chances of randomly walking all the way out to the end become even more negligible. And so the question we're going to have to ask ourselves is, what do we have to do differently to our random tester to make sure it tests this situation as thoroughly as it tested this situation? And so there's no cut and dried answer to this kind of question. These kind of questions definitely are hard in practice. And when something changes about the software under test, we might have to adjust the probabilities to compensate. And so let's just look at one possible solution. One possible solution would be to bias the probabilities towards n queuing. So if the random number generator returns a number less than 0.6 instead of 0.5, we're going to n queue, and the other 40% of the time, we're going to dequeue. So let's see what effect that has. So this time, we attempted to add elements to a full queue a large number of times, but this time we seem to have not particularly well tested the case of removing from an empty queue. And let's run it a couple more times and see what happens. Yeah, see, this time we didn't remove from an empty queue anytime. So we biased the probabilities too far towards adding. And what's going to happen is, in any kind of a random walk is, as long as the probabilities are respectably balanced, it's going to take a long time to get somewhere unless we unbalance the probabilities significantly, like we did with this 60-40 distribution. What I'd probably do in this case is make a configurable bias to the probability, and now add a completely new random testing loop. And now we're going to set that bias variable to be something sort of large, unless x is odd. If x is odd, we're going to set the bias variable to be something less. Okay, so let's look at what we did. We took our random testing loop and we enclosed it in a larger random testing loop. And in that larger random testing loop, we sort of made a qualitative change to one of the probabilities. That is to say, we biased execution towards one of our API calls in favor of the other, and on even numbered calls, we biased it the other way. So what we're hoping to do now is create a situation where we start off in the empty state, we migrate with pretty high probability towards full and bounce around there. And then at the end of that particular configuration of the testing run, we're going to walk back. We're going to do that, I believe, 20 times. And so what we hope is that this will test, even for the fairly large queue, a lot of its possibilities. So let's see if that actually happens. So of course it's going to take longer to run this time.